There are echoes in the universe we can't hear, but space can. A collision between two supermassive black holes, so violent it warped time and space, has just been detected. But what really collided out there in the dark? Chapter 1: The Bigger Picture. Black holes are not alone. For a long time, black holes were thought to be silent, solitary beasts lurking in the dark corners of the universe, swallowing light and giving nothing back. They were seen as cosmic endpoints, places where matter disappears forever. But that picture was never complete. Black holes are not alone. They collide, they merge, and when they do, the entire fabric of space shakes. Recently, scientists detected something extraordinary. A gravitational wave unlike anything we've recorded before. A ripple in spacetime caused by two massive black holes spiraling into each other and becoming one. And this wasn't just another black hole merger. This one was the most massive ever observed, a true cosmic event that has left scientists stunned. Let's step back for a moment. Imagine two black holes, each many times heavier than our sun. They orbit each other in the void, pulled together by gravity in a deadly dance. For millions of years, they spiral closer and closer, until the moment of impact, when they crash and merge into a single, even more massive black hole. That final moment releases more energy than all the stars in the universe combined. For just a brief second, we never see this with our eyes, but we hear it through gravitational waves. This particular event, known as GW190521, happened about 7 billion years ago. The signal reached Earth only recently. It came from a time when the universe was just half its current age. The two black holes involved were huge, one around 85 solar masses, and the other 66. Their collision formed a new black hole, with a mass of about 142 suns. That means 9 solar masses worth of energy was released instantly. That's an explosion of pure gravity strong enough to ripple across billions of light years and still be detectable here on Earth. Now, what makes this even more mysterious is that black holes of these sizes aren't supposed to exist. There's something called the parent stability mass gap. It's a range between about 65 and 120 solar masses where black holes shouldn't form through normal star collapse. Stars that big should explode completely, leaving nothing behind. Yet here we are with a black hole that seems to have broken the rules. This is why GW190521 is so important. It challenges what we thought we knew about black hole formation. It suggests that some black holes, maybe even many, are born not from dying stars, but from the collision of other black holes. A chain reaction. One merger leads to another, growing a black hole larger and larger over cosmic time. This kind of event tells us that the universe is far more dynamic, far more violent than we imagined. It also tells us something deeper, something humbling. These colossal collisions happened long before Earth formed, long before the sun was born, long before any eye could see or any ear could hear. Yet now, through delicate instruments and decades of human effort, we are finally hearing the echoes of ancient cataclysms. Think about that for a second. We've built machines on Earth that can detect a faint ripple in space, caused by two black holes merging 7 billion years ago. That ripple passed through your body, your city, your planet, subtle, silent, and invisible. But it was real. It bent space itself. In that moment, we didn't just observe a black hole. We heard the universe speak, and it spoke in a deep, low frequency, hum lasting just 1/10 of a second. A sound too deep for human ears, but unmistakable to the instruments at LIGO and Virgo. The twin gravitational wave observatories responsible for this discovery. For many scientists, this wasn't just a new detection, it was a milestone. The first clear observation of an intermediate mass black hole, sitting between the well-known stellar black holes and the supermassive giants at the centers of galaxies. It opens new doors. Where did these intermediate black holes come from? Could they be the building blocks of the supermassive ones? Could early galaxies have formed around them? Each answer leads to more questions. But for now, what we do know is this: black holes are not quiet relics of the past. They are active agents in the universe, growing, merging, roaring. Their gravity shapes galaxies. Their collisions echo across time, and we are just beginning to listen. In the chapters ahead, we'll look deeper into the science of gravitational waves, the mystery of why these collisions don't match our models, and what this might mean for our understanding of dark matter, extra dimensions, and the early universe. But here, at the start of our journey, it's worth pausing, because this single event, GW190521, is not just a discovery, it's a reminder that the cosmos is alive, that space is not empty, but full of motion and memory, that even in the cold silence of the void, there are moments of immense violence and beauty, and that somehow, against all odds, we are able to witness them. So the next time you look at the night sky, remember this: there may be two black holes, somewhere out there, spiraling toward each other, and when they finally collide, the entire universe will listen. Chapter 2. Why this discovery changes everything. When scientists first looked at the data from the event, now known as GW190521, something felt off. At first glance, it looked like another black hole merger, but then the numbers started raising questions. The signal was unusually short, lasting just 1/10 of a second. It didn't match the familiar patterns that researchers had seen in previous collisions. It was louder, heavier, and stranger. And then came the real shock: the size of the black holes involved. One was about 85 times the mass of our Sun, the other 66 solar masses. Together, they formed a black hole with 142 solar masses. The first clear evidence of what scientists call an intermediate mass black hole. Until that moment, this size range was only theoretical. No one had ever seen one before. But there was a problem. According to current models of how stars die and form black holes, a black hole with 85 solar masses shouldn't exist. It falls right into what astrophysicists call the perinstability mass gapper, mysterious no man's land, where stars of certain sizes are supposed to explode completely, leaving nothing behind, not even a black hole. In theory, when a star gets to massive somewhere between 65 and 120 solar masses, it becomes unstable due to something called pair production. High-energy photons in the star's core create pairs of electrons and positrons. This weakens the pressure that holds the star up against gravity. As a result, the star collapses and detonates in a massive explosion, scattering its contents across space. No core remains, no black hole is born. So how, then, did we get a black hole at 85 solar masses? The only likely explanation is that this black hole wasn't born from a star at all. It was born from another black hole merger. This idea changes everything. It means that black holes can build upon each other, merging again and again, climbing up the mass ladder with each collision. Over billions of years, these repeated mergers might even be how the enormous supermassive black holes at the centers of galaxies are born. Until now, scientists believed that supermassive black holes formed either very early in the universe or through the slow, steady growth of smaller ones. But GW190521 introduces a third possibility: black hole cascades, where a series of mergers creates larger and larger black holes in a relatively short time. This also changes how we think about the environment these events happen in. For two black holes to merge, they have to be close enough to each other and isolated from interference. But for a black hole to merge again after an initial collision, it needs to exist in a dense, dynamic region of space, where gravitational interactions constantly push massive objects together. Such places might include the crowded cores of globular clusters, or the centers of galaxies where stars and black holes move like particles in a cosmic storm. In these environments, black holes could pair up, merge, and then do it again. GW190521 might be the first clear sign that these second-generation mergers are real, that black holes are not just passive remnants of dead stars, but active players in the evolution of the universe. And this leads to even bigger questions. If black holes can grow through repeated collisions, could they reach even more extreme sizes without needing stars at all? Could some of the supermassive black holes we see today, millions, or even billions of times heavier than the Sun, have formed entirely from mergers, without ever having started as stars? That would rewrite the story of how galaxies form and evolve. But there's another puzzle: the shape of the gravitational wave itself. Most black hole mergers detected by LIGO and Virgo have a clear, predictable signaler kind of chirp that rises in frequency as the two objects spiral closer. But GW190521 wasn't a chirp. It was more like a thundershort, low-frequency burst. Some scientists have suggested that this odd shape could mean the black holes were spinning rapidly, or that they collided at an unusual angle. Others wonder if the signal might have passed through curved regions of space caused by massive objects, distorting it before it reached us. There are even more exotic ideas. Some theorists have asked whether this signal could be a hint of extra dimensions, or even a sign of physics beyond Einstein's theory of general relativity. While these ideas are still speculative, they show just how disruptive GW190521 really is. It doesn't fit. It refuses to be explained easily. And in science, that's usually a good sign. It means we're standing on the edge of something new. What makes this moment even more remarkable is how we found it. Gravitational wave detectors like LIGO and Virgo are incredibly sensitive. They use laser beams, shot down long tunnels for kilometers in length, that bounce between mirrors. When a gravitational wave passes through Earth, it stretches space in one direction and compresses it in another. The lasers detect this tiny change, smaller than the width of a proton. It's hard to believe, but with this precision, we're listening to the rhythm of the cosmos. When GW190521 was detected in May 2019, it took months of analysis before scientists confirmed what they had. The wave was so unusual, it wasn't even obvious that it came from a black hole collision. But after careful modeling and simulation, the pieces fit. Still, questions remain. What caused the strange shape of the signal? Where exactly did the merger happen? And how common are events like this? One thing is clear, this wasn't a fluke. As gravitational wave science advances, we're likely to find many more collisions like this, some bigger, some even stranger. Each one will tell a different story. Each one will challenge what we know. And somewhere out there, perhaps right now, another pair of black holes is drawing closer. Another collision is waiting to send its voice across the cosmos. We just have to be ready to hear it. Chapter 3. The gravity that shapes galaxies in the vast emptiness of space. Gravity is the silent sculptor. It doesn't shout or flash. It doesn't explode like a supernova or beam like a quasar. Instead, it pulls steadily, invisibly shaping the cosmos over billions of years. And at the heart of nearly every galaxy, including our own Milky Way, lies a supermassive black hole. These monstrous objects don't just consume matter, they control the destiny of entire galaxies. The idea that something so destructive could also be a source of order might seem strange. But black holes aren't just cosmic vacuum cleaners. In fact, they might be the reason galaxies form the way they do. Astronomers have found a mysterious connection between the mass of a galaxy's central black hole and the overall mass of its bulge. The bigger the black hole, the bigger the galaxy. This link, known as the M-sigma relation, hints that black holes and galaxies evolved together. It starts with the early universe's sea of gas, dust, and dark matter. Regions of slightly higher density begin to collapse under gravity. Stars form. Clusters of stars gather into galaxies, and near the center of these clusters, black holes grow, feeding on gas and merging with others during galactic collisions. As they grow, they begin to influence their surroundings in powerful ways. One way black holes shape galaxies is through feedback process, where the energy released by a black hole affects the gas around it. When matter falls into a supermassive black hole, it doesn't disappear quietly. The intense heat and friction in the accretion disk around the black hole cause the material to emit massive amounts of energy. Some of this energy escapes in the form of jets, narrow beams of particles shooting out from the poles of the black hole at nearly the speed of light. Others come out as intense radiation. This feedback can push gas away from the galactic center, slowing down star formation. Without gas, stars can't form, and the galaxy's growth stalls. In this way, black holes regulate their own galaxy's feeding just enough to grow, but powerful enough to keep the galaxy from growing too fast. It's like a cosmic thermostat. We see this process clearly in active galactic nuclei, or AGN. These are galaxies with supermassive black holes that are actively consuming matter. The jets and radiation from AGN can be so powerful that they light up entire galaxies, outshining all their stars combined. And those jets can stretch across hundreds of thousands of light years, plowing through intergalactic space, heating gas, and disrupting the environment around the galaxy. But not all black holes are this active. In fact, most of the time, supermassive black holes lie quiet and invisible, like sleeping giants. The one at the center of the Milky Way, Sagittarius A*, is a perfect example. It's about 4 million times the mass of the Sun, yet it emits only a tiny trickle of radiation. But its presence can be felt. It holds the center of the galaxy together, anchoring stars that orbit at mind-bending speeds. Without it, the galactic core would fly apart. Even though black holes themselves are invisible, we can trace their influence by looking at the motion of stars and gas around them. The orbits of stars near Sagittarius A* were one of the first solid pieces of evidence that confirmed the existence of a supermassive black hole. These stars move incredibly fast, some completing orbits in just a few decades, far too fast for anything other than a massive, compact object to be pulling on them. Over cosmic time, galaxies collide and merge, and when they do, their central black holes often meet, forming even more massive black holes. This process creates gravitational waves, ripples in the fabric of spacetime, that we are only now beginning to detect with instruments like LIGO and Virgo. These waves tell us about the final moments of black hole mergers, giving us a new way to observe the invisible. What is perhaps most fascinating is the idea that black holes might act as seeds for galaxy formation. Some theories suggest that massive black holes formed incredibly early in the universe, just a few hundred million years after the Big Bang. These early black holes may have helped gather gas and dust, triggering the birth of stars and galaxies much faster than we once thought possible. If that's true, then black holes aren't just a part of galaxies. They are the reason galaxies exist at all. In this light, the image of a black hole transforms. It's no longer just a monster lurking in the dark. It's an architect, a regulator, a source of order amid chaos. Through their immense gravity, black holes guide the structure of the cosmos. From the swirling arms of galaxies to the limits of star formation, they are the unseen hands behind the elegance of the universe. So when we look up at the night sky and admire the Milky Way stretching across the heavens, we're really seeing the fingerprints of a black hole. Without Sagittarius A*, we might not have a galaxy at all. We might not have stars. We might not have planets. We might not have life. This is why the study of black holes goes beyond curiosity. It touches the deepest questions of cosmic structure and human existence. These silent, invisible giants are not just endpoints of stars. They are fundamental to how the universe came to be. In the next chapter, we'll journey into the dark future. What happens to black holes in the end? Do they last forever, or do they eventually vanish? And if everything else fades into nothing, will black holes be the last things left in the universe? Let's find out. Chapter 4. The Paradox of Infinite Power. Let's pause for a moment. When we talk about something being the most powerful in the universe, we're usually tempted to think in straight lines. Bigger is better. Faster is stronger. But the cosmos doesn't play by those rules. What if the most powerful force isn't something we can measure by sheer size, mass, or energy output? What if true power lies in influence in space, on time, on matter, and even on the boundaries of what we understand as reality? Let's return to black holes, particularly supermassive black holes. These titans don't just consume matter, they shape galaxies. At the center of nearly every galaxy lies one of these monsters, including our own Milky Way. The black hole at its center, Sagittarius A*, holds a mass over 4 million times that of our Sun. It's like a cosmic puppeteer, subtly orchestrating the motion of hundreds of billions of stars in its galactic dance. It's invisible, silent, and yet utterly dominant. But here's the paradox. Black holes are known for destroying. They consume light, crush matter, and collapse stars into oblivion. And yet, their very presence seems essential for creation. Galaxies form around them. Matter swirls into accretion disks, heats up, and produces radiation that lights up the cosmos. Could it be that destruction and creation are simply two faces of the same force? This isn't just a philosophical twist. It's observable. The jets from black holes streaming out at near light speed carry material and energy across vast cosmic distances. These jets regulate star formation in galaxies. Too much gas in a galaxy, and stars would form too rapidly, destabilizing the structure. But black holes eject that gas outward, slowing star birth, keeping balance. So something once thought to be only a devourer is, paradoxically, a cosmic gardener. Now consider time. Near a black hole, time itself distorts according to Einstein's general theory of relativity. Gravity bends spacetime. The stronger the gravity, the slower time moves. Near the event horizon of a black hole, time crawls to a stop. From a distance, you'd never see an object cross the event horizon. It would freeze, forever suspended. But to the object itself, time would continue as normal, until it vanishes into the unknown. This bending of time isn't just theoretical, it's measurable. We observed clocks tick more slowly on satellites, further from Earth's gravity compared to those on the ground. It's a tiny effect here, but near a black hole, time dilates dramatically. In a real sense, black holes don't just shape space, they command time. What could be more powerful than controlling the flow of time itself? But let's zoom out even further. Black holes also challenge the very structure of knowledge. At their core lies the singularity, a point of infinite density, where our laws of physics collapse. It's not just that we don't understand what happens, there we can't. Space, time, matter, and even information lose meaning. It's a wall, a boundary where science currently stops. In this way, black holes are not just physical entities, they are intellectual frontiers. They mock our equations, resist our simulations, and remind us how little we truly know. And then there's Hawking radiation. The revolutionary idea, proposed by Stephen Hawking, suggests that black holes may not live forever. Over immense timescales, they can evaporate, particle by particle, through quantum effects at the event horizon. This small, quiet leak of energy might eventually erase even the most monstrous black holes from existence. And if that's true, then even the most powerful thing in the universe is still temporary, which leads us to a final paradox. How can something be the most powerful if it is ultimately doomed to vanish? The answer may lie in perspective. Perhaps true power doesn't come from permanence. Perhaps it comes from impact. Black holes affect stars, galaxies, light, time, and human understanding. Their fingerprints are found across cosmic structures and philosophical questions alike. They have the ability to create, to destroy, to challenge, and to redefine. In this way, they transcend the typical definition of power. And yet, even as we explore them, building telescopes, like the Event Horizon Telescope, running simulations, studying gravitational waves, we are only beginning to scratch the surface. Black holes don't just pull on matter, they pull on our curiosity, on our imagination, on our sense of what's possible. They ask us, what is reality, really? Where does it begin and where does it break? So perhaps, the paradox of infinite power is not a contradiction. Perhaps it's a doorway, one that invites us to step into deeper questions, into deeper awe. After all, the most powerful thing in the universe may not just be out there, it may be the pursuit of understanding it. Chapter 5. The Ultimate Limit. What lies beyond the event horizon? We followed the journey from the vast influence of supermassive black holes to their mysterious births and their colossal power. But there's one boundary we haven't crossed yet, one that no spacecraft, no light, and no information can return from. The event horizon. It's the edge of the unknown, the surface of no return. But what lies beyond it? What happens inside a black hole? To understand that, we must revisit what the event horizon really is. Imagine a place where gravity is so strong that nothing, not even light, can escape. The event horizon marks that invisible border. Once anything crosses it, it's cut off from the rest of the universe forever. But the real mystery begins inside. According to Einstein's general relativity, once you fall past the event horizon, you're pulled toward the singularity, an infinitely dense point where space and time break down. But here's the problem. General relativity works well on the large scale of stars and galaxies, but not at the quantum level. To truly understand what happens inside a black hole, we need a theory that merges gravity with quantum mechanics, a theory of quantum gravity. Right now, we don't have that. This is where black holes become more than just astronomical objects. They become testing grounds for the deepest questions in physics. One such question is, does information survive a black hole? Stephen Hawking once suggested that anything falling into a black hole is lost forever, erasing information from the universe. But this idea contradicts quantum theory, which says information must be conserved. This conflict sparked the black hole information paradox, one of the biggest unsolved problems in theoretical physics. Recent ideas try to resolve this paradox. Some physicists suggest that information may be stored in the event horizon itself, encoded in subtle quantum patterns, something like a cosmic hologram. Others think black holes could slowly leak information through Hawking radiation, the faint glow black holes emit as they slowly evaporate over time. If this is true, black holes aren't completely black, they're whispering secrets back into the universe. Another radical idea is the concept of wormholes. If black holes and their opposite, white holes, are connected, they might form a tunnel through spacetime, a shortcut between distant parts of the universe. Science fiction, maybe, but math allows for the possibility. If wormholes exist, they could be the key to faster-than-light travel or even time travel, but they're also unstable and might collapse instantly unless held open by some exotic, negative energy matter we've never seen. Some theories go even further. They suggest that the interior of a black hole may not be a singularity at all, but another universe. Just as our universe might have been born from a black hole in some larger cosmos, maybe black holes in our universe spawn entirely new realities, each with its own space, time, and physics. If that's true, every black hole could be a cosmic seed, a gateway to a new universe. But these ideas remain speculative. We have no way to peek behind the event horizon. Not yet. Our telescopes can only see the outlines, only the shadows black holes cast against glowing gas and plasma. But even that shadow tells a powerful story. When we captured the image of the black hole in galaxy M87, it wasn't just a scientific achievement. It was a glimpse into a realm beyond human reach, beyond light, beyond time. Standing at the edge of a black hole, we face the ultimate limit of human knowledge. It's a wall not of stone, but of understanding. Every time we point a telescope toward the heart of a galaxy, every time we measure gravitational waves rippling from black hole mergers, we're knocking on that wall, hoping to hear an echo. We may not yet know what lies beyond, but we're getting closer. In the end, black holes force us to confront the boundaries of our reality. They challenge our most trusted theories. They humble our ambitions. And yet, they inspire our greatest questions. So we return to the question we began with. What is the most powerful thing in the universe? Maybe it's not just the energy of a supermassive black hole, or the immense gravitational pull it exerts. Maybe it's the mystery itself. Because nothing moves us more than the unknown. The edge of the event horizon is also the edge of imagination, of wonder, of the very spirit of science. And perhaps that's the most powerful force in the universe. If the mysteries of space make your mind wander like ours, consider subscribing. Like the video if you felt that sense of cosmic awe, and share your thoughts in the comments. What do you think lies beyond the event horizon? Let's keep exploring the unknown together.